Hey everybody, so in this video I'm going to be talking to you about electronegativity and giving you a little intuition on what it means and how it works. So the prime definition of electronegativity is basically the atom's hunger for an additional electron. How, or its desire for an additional electron. So it's basically how bad or how much an atom wants another electron. So the general trend, all right, so the general trend would be, let me pick a different color. So as you go up and move to the right like that, the electronegativity increases. So it increases uh, with this orientation of these red arrows. So as you go up and to the right, and so you expect the top right, in the upper right corner right here we have fluorine. So this is the most electronegative element. So the reason why we're not choosing the noble gases is because if you look at the noble gases, their outermost shell, their last orbital is completely full. For example, let's say neon would be right here under helium. So if you draw out the electron configuration for neon, it would be 1s squared, 2s squared, and then 2p6. So if you look at the outer shell, the valence shell. So let's say this is the nucleus, and you have the first shell and then the second shell. All right, so the first one has 1 and then 2, and then the second one would have 1, 2, 3, 4, 5, 6, 7, 8. So it's happy, it's stable the way it is, having a full orbital, a full shell, and that's the reason why we don't consider them when thinking about electronegativity. And so fluorine comes in first place. So you would the electron configuration for fluorine would be 1s squared, 1s squared, 2s squared, 2p5. You see this, the p orbital. So if you draw that right out here, right here, so that would be. Let me move here. So if you draw that out, you would, in the 2p orbital, right, it has 3, so that's 1, 2, 3, 4, 5. So this last position right here, it needs one more electron and it would be a completely filled p orbital. And that's the reason why, because it's so close to being completely full, it really wants that last electron so badly. So that's a little intuition how to think about this. And then, so you might ask, what if we go down? What if we go down a group instead of moving to the right of a period? So when you move down, all right, so when you move down, the atoms get bigger as you add more shells. Okay, so let's say cesium's all the way down. And then so you have all these shells, and then you find the valence electron. Well, if you look at what group it's in, cesium only has one valence electron. So let's say this is the outermost shell and it has one valence electron right there. Because it's so far away from the nucleus, and the nucleus is where you have the attraction force, there's so many shells, inner shells, core shells, that that do the phenomena as shielding. All right, they're doing so much shielding that this valence electron all the way out does not feel that much of a attractive force to the center. So it's so easy to take that electron away, which is the opposite of what electronegativity is. Electronegativity is how much it would want to accept an electron, gain another electron. Here, this cesium, it could get rid of this electron just so easily as it's placed all the way back down here, which is the opposite of the trend of electronegativity. And that's the reason why, as the atoms get bigger, their electronegativity decreases. So in general, you could think of the trend as it goes up and to the right, with fluorine being the most electronegative.